All right, well, welcome back. So in this section, we're actually going to start off by looking back on this idea of solving some of these different types of congruences. And then in this process, we're actually going to start to see where this idea of Fermat's little theorem can actually be used to find some of these inverses. This idea is actually going to springboard us into the slightly more general study of inverses and ultimately this question of looking at RSA encryption. So to start this thing off, we're going to be looking at this little problem that simply says, I want to solve this congruence that looks like 5x being congruent to 3 mod 17. So we know this idea is basically going to boil down to this question of, can I find something that when I multiply it by 5, it's going to kick out a 1 mod 17? So in this case, what we're looking for is we're looking for the inverse of 5 modulo 17. So in this case, we actually have one idea of how to solve this thing, and this is going to be through this notion of this extended Euclidean algorithm. So what I want to do is I want to look at these numbers 17 and 5, and I want to see that the greatest common divisor between these two things is in fact 1, and then I want to run this thing backwards to actually find those key little weights that I'm going to have something that's going to say 5 times something plus 17 times something else is going to kick out a 1. Once I have that key little equation, I can reduce that thing modulo 17 and really see exactly what that inverse of 5 is going to be. So in this case, let's just run that thing really quickly just to kind of get us a little bit more practice on seeing all of these little steps come into play. So in this case, we're looking at 17, which is the larger of those two numbers. So I'm going to put that one first, comma 5. So in this case, I'm going to try to think about how many times does 5 go into 17? And in this case, I know that 5 times 3 is 15. And in this case, if I add 2 more to that thing, it's going to jump me up to 17. So in this case, I'm going to have 17 is going to be a 3 multiplied by a 5. So there's my 15 plus a 2. And then rerunning this thing on the new pair, which is the pair 5 comma 2, you're going to see that I'm going to stop pretty quickly. So in this case, 5 is going to be 2 times 2, which is 4, plus a little 1. So in this case, you can see that little remainder of a 1 popping up, which is going to tell me that those two numbers, which we already know are going to be relatively prime, are in fact going to be relatively prime. So in this case, I'm going to have my new pair, which is a 2 and a 1. And if I really wanted to formally see the last little step in this thing, I could rerun this thing one more time to see 2, which is 2 times 1. And there's my remainder of a 0. And that's going to be my key stopping place. The moment that I see that remainder of a 0, I'm going to double back to look at the last non-zero remainder. So in this case, I can see that that last non-zero thing is a 1. So in this case, I do know that the GCD between 17 and 5 is in fact 1. So they are in fact relatively prime. And then if I run this thing in reverse, I can actually find those key little weights. So that second to last little step is going to tell me that 1 is going to be a 5 minus a 2 times a 2. And then I'm going to substitute in what that little 2 is using that top equation. So in this case, I'm going to have a 5 minus a 2. In this case, it's going to be a 17 minus 3 times a 5. And then doing a little bit of distribution is going to say 2 and a 17. There's a negative 2 with 3, which is a positive 6 and a 5. In this case, I have 1 5 over here, so it's a 5 times a 1. And there's going to be 6 of them over there, which tells me in total I'm going to have 7 of those things. And then there's this little negative 2 and a 17. So in this case, what I end up having is that I'm going to have 5 times 7 plus a 17 times a negative 2 is going to kick out a 1. So if I look at this big key equation, if I do this reduction modulo 17, I know that that 17 right there is going to turn into a 0 in this mod 17 world. So what I end up seeing is that I'm going to see something like a 5 times a 7 is going to kick out a 1 mod 17. So in this case, that's exactly what I was hoping to see. I wanted to see 5 multiplied by some number. So in this case, that number is going to be a 7. And I want that thing to kick out a 1 in this mod 17 world. So in this case, the little y in quotes that I'm looking for is simply this nice little number of 7. So now when I go back to actually trying to solve this little equation, so I'm going to go ahead and actually try to see if I can change my colors, which maybe I can't right now. So I'm just going to leave it as blue, I guess. What I'm going to do is I'm going to go back to this little congruence that I started with. So 5x being congruent to 3 mod 17. What's going to happen is that I want to get rid of that little 5. So what I'm going to do is I'm going to multiply both sides of this congruence by a 7 because I know that 7 and 5 are going to be inverses of each other. So in this case, 7 on the left-hand side and a 7 on the right-hand side. And then I'm still going to be doing this stuff modulo 17. The 7 times the 5, I know that's going to kick out a 1 by that little inverse line that I have down here. So that 7 and that 5, they're going to combine to make a 1. So the left-hand side of this thing is simply going to say 1 times an x. And then that right-hand side is going to say 7 times 3, which I can compute as being a 21. So in this case, 21 modulo 17. If I wanted to, I could actually reduce this a little bit farther. This idea that that left-hand side is simply just going to say x, and 21 modulo 17, that's simply going to turn into a 4. So I'm left with this little statement that's going to say any x's that have the potential of being 4 modulo 17, they are going to solve this congruence. So in this case, you could go back and check if you plugged 4 into that thing, you'd have 5 times 4, which is 20, and 20 modulo 17 is in fact 3. So we know that we have one solution, in this case 4, but the idea is that I could add or subtract 17 as many times as I wanted to and continually kick out different solutions in this situation. Okay, so that's one way of attacking that thing. So that's kind of this classic first version that we saw back in the beginning of this topic. What I'm going to do now is I'm going to chat about another version of solving this thing. Basically, the question is going to boil down to this idea of, do I have another way of actually finding this special y that's going to get rid of that 5? So the idea is that I want to find the inverse of 5 modulo 17. So in this case, the last way is that we ran this extended Euclidean algorithm and we got this big kind of messy linear combination that actually told me what those little weights had to be, and then that said actually what the inverse of that thing was. Well, we also have a nice little fact that's going to give us a slightly faster way of finding this inverse, but there's going to be its own little downside. So what we're going to be doing in this situation is we're going to be invoking Fermat's little theorem. So in this case, I'm going to really quickly just show you what Fermat's little theorem said. We saw this back in the section on induction. It's this idea that if you give me some prime number, if I take any number and raise it to that prime, so in this case, if I'm looking at, so in this case, modulo 17, well, if I take something like a 5 and raise it to the 17th power, what's going to happen is that it's going to kick out that 5 again. So this is going to be done modulo 17. So that's this pretty slick little result that we looked at back in that section on induction. You saw a few different homework problems along the way that had you do a few special cases of this for different types of small prime numbers. Some of them become these nice case arguments where you just try to run through a whole bunch of little numbers less than that 17, seeing what little powers are going to get kicked out. There is actually a really special consequence of this Fermat's little theorem, which basically says the exact same thing up here, but what's going to happen is I'm going to reduce all those powers by 1. So in this case, rather than looking at a 15 to the 17th power, I'm going to look at a 5, or I should say a 5 to the 17th power. I'm going to look at a 5 to the prime power minus 1. So in this case, if I look at a 5 raised to the 16th power, what's going to happen is that that thing on the right-hand side is also going to reduce by 1 power. So in this case, it's now a 5 to the 1. What's going to happen is it's going to become a 5 to the 0, which is a 1. So in this situation, you can see that 5 to the 16th power is in fact going to kick out a 1, and that's going to be done modulo 17. And that's the pretty slick little result. You can see that I'm going to have some things that are going to create a 1. And anytime I see these little 1s, that's where this inverse alarm is going to be kind of firing. It's going to be yelling at you saying, hey, there's actually some inverses hiding here. So that's the result that I'm going to take back to that previous example to try to see another one of these little inverses come into play. So what's going to happen is that I'm going to look for something multiplied by 5, kicking out a 1. Well, by Fermat's little theorem, what I'm going to have is I know that 5 raised to the 16th power, so that prime number minus 1, is going to be congruent to 1, and that's going to be done modulo 17. What's going to happen here is I'm going to break off 1 power of this 5. So I know that 16 can be viewed as a 15 plus 1. So what I can do is I can rip off one of these things. So the idea is that it's going to be 5 to the 1 plus a 16, 1 plus a 15, I can add. And that's going to kick out a 1, and that's going to be done modulo 17. In this case is going to be one of our properties of exponents, the idea that if I have a to the m plus m, this is a to the n, a to the m. So I'm going to rip off one of those things. This is going to be 5 to the 1, and then a 5 to the 15th, and that's going to kick out this 1, modulo 17. So in this case, you can see that's exactly what I wanted to see. I now have 5 multiplied by a 5 to the 15th is going to be a 1, modulo 17. So that is, again, the exact same thing that I wanted to see up above. I wanted 5 multiplied by some number, so in this case, this is my some number, that's going to kick out a 1. That some number in this case is a little bit worse looking than that last one, but I know it exists, and that's all I care about in this situation is that I can find one of these crazy little objects. So in this case, if I go back to actually trying to solve this little congruence, I'm going to start this thing off with a 5x being congruent to a 3, modulo 17. I'm going to multiply both sides by this inverse of 5. And in this case, I know another version of this inverse is going to be a 5 to the 15th power. So in this case, giving both sides a 5 to the 15th power. So that's on the left-hand side, and on the right-hand side, it's going to do the exact same thing. what's going to happen is that I know that this 5 to the 15th multiplied by another 5 is going to turn into a 5 to the 16th. So it's again combining those two exponents. The 15 plus the 1 is going to add up to a 16. There's still going to be an x on that left-hand side, and then I'm just going to leave this right-hand side as this kind of big giant mess. So in this case, it's going to be a mod 17. Okay, so 5 to the 16th I know is going to kick out a 1. That's this Fermat's little theorem coming into play. So that left-hand side is going to say x, or just simply a 1 times an x, which is going to be a 5 to the 15th. I can read my own handwriting, I guess. All right, so 5 to the 15th multiplied by a 3, and then this is going to be a mod 17. So this is where this approach has a pretty big downside. You can see that the right-hand side of this expression is pretty gross looking. The left-hand side simply says an x. And then that right-hand side is going to be some pretty big number. If you actually go ahead and try to compute 5 to the 15th power, depending on the calculator you're working with, you might get some gigantic exponential notation because it's going to be a huge number. So what's going to happen is that if you take that gigantic number and reduce it modulo 17, it is in fact going to kick out a 4, which is what you're hoping to see. So like I said, it's not so great if you don't have some more sophisticated piece of technology that can do some of these large exponents via modular arithmetic, kind of this reduction modulo 17. But in this case, it does actually give us a solution. The idea is that I can actually take these things, multiply by something. In this case, I know that that inverse is going to exist. And then if you have the capabilities of actually reducing it, you can go ahead and reduce it.